Hello and welcome everyone to the presentation of the paper Detection and Retrieval of Out-of-Distribution Objects in Semantic Segmentation. It is a pleasure to introduce my co-worker Matthias Rottmann from the University of Wuppertal and my supervisor Gernot Fink from TU Dortmund University. My name is Philipp Oberdiek and I will guide you through this presentation. The outline of the presentation will be as follows. After starting with the motivation, we will briefly introduce the method we used for the detection of new concepts and prove its performance during domain shift. Following this, we show how to utilize the detected objects and assess their relevance. This will be guided by a quantitative and qualitative evaluation. Afterwards, we will summarize our proposed pipeline and give a demo presentation of our implementation. The talk will be finalized with a glance on future work. In the real world, many different deltas or sources of domain shift exist. Even when we restrict the environment to road traffic, there are numerous causes of domain shift. The visual world's inherent change in time, either over a long or a short term, already introduces a huge variability. Furthermore, changes in weather condition can rapidly alter the appearance of objects. Even a simple change in location can have a dramatic effect on the type and look of objects that can be perceived. These problems led us to our guiding question for this publication. How can we reliably detect new concepts and understand their relevance? Starting off with the task of the detection of new concepts, we utilized a meta-segmentation approach that only relies on dispersion measures and geometric properties of the output of a neural network. Using these dispersion measures, which are also aggregated using geometric properties of a segment, we train a second shallow neural network to predict the intersection over union of a predicted segment with the ground truth. On this panel, you can see the entropy heat map of the softmax output on the top left, the predicted intersection over union on the top right, with red indicating a low and green a high predicted IOU, the predicted segmentation mask on the bottom right, and the original image on the bottom left. By cropping and gathering segments which have an estimated IOU of less than 0.5, we can collect objects that are likely to be badly segmented by the segmentation network. Our assumption is that objects that are unknown to the segmentation network are also getting a poor predicted segmentation mask. Before continuing with the quantitative results, we give a brief overview of our experimental setup. As semantic segmentation model, we used a state-of-the-art DeepLab v3+, which was trained on the Cityscapes dataset. The Cityscapes dataset, which consists mainly of images in urban environments, serves as our in-distribution dataset. We chose the A2D2 dataset as our out-of-distribution dataset because besides images from urban environments, it also contains scenes from the countryside and additional object classes, which makes it highly suitable to simulate a domain shift. We randomly sampled 2,000 images out of the approximately 31,000 images and additionally included all images containing tractor instances. In order to investigate the effectiveness of the meta-segmentation approach on data which is different from the training dataset, we performed some experiments. In our first experiment, we evaluated the IOU of segments which have a predicted IOU below a given threshold. Varying the threshold leads us to the graph on the left, which shows us that the meta-segmentation approach is indeed able to detect out-of-distribution segments that have a low IOU with the annotation. The performance on the A2D2 dataset is close to the one on the in-distribution dataset. As a second experiment, we evaluated if unknown object classes are detected reliably. We restricted all segments to have a minimum size of 128 by 128 pixels and collected detection rates for different A2D2 classes. As you can see, the tractor class, which is unknown to the segmentation network, has a very high detection rate. Other classes like roadblocks, which also contain highway fences, or the truck class, which contains many large trucks, mostly occurring on the highway, are also detected very well. On the other hand, object classes that are already known to the segmentation network, like for example pedestrians or cars, are not detected. Evaluating the number of detected objects per image leads us to 0.06 objects per image on the Cityscapes test dataset and 0.82 objects per image on the A2D2 dataset, which further proves the effectiveness of the approach under domain shift. The next step in the pipeline is to assess the relevance of the previously detected objects. We propose to use a standard convolutional neural network, like for example VGG16, which was pre-trained on an object detection dataset like ImageNet. By using the encoder part of this network only, we can extract visual features of the detected objects. In order to make the features more accessible for humans, we reduce the dimensionality of the feature vectors by using standard approaches like a principal component analysis or t-SNE. The resulting embedding space can be analyzed in terms of relevance by using retrieval. Before we continue with the quantitative retrieval results, we want to give a complete overview of our pipeline and also show our demo application. Starting with the predicted segmentation, we rate all segments by predicting the IOU based on dispersion measures and geometric properties. Segments with a predicted IOU of less than 0.5 are cropped out of the original image. Utilizing the encoder part of a pre-trained object detection network gives us feature embeddings for all detected objects. After reducing their dimensionality to preserve only meaningful features, we can make them accessible for humans. The data exploration can be enhanced by using retrieval in the resulting embedding space. Let us point out that the method for rating the predicted segments, as well as the choice of the embedding network and its training dataset, is of generic nature and can be replaced by other approaches. The advantage of the used meta-segmentation approach is the rating of whole segments, which is in contrast to many other methods that predict confidence on a pixel level. At this point, let us give you a presentation of our demo application. This is a demo of our data exploration tool, which was specifically designed for the usage under domain shift. So this is what it looks like when someone wants to find new object classes, for example. You can show an estimated global density in the background. And like that, you can already see 3 clusters which have higher density. Speaking of clusters, you could also use k-means clustering, for example, in this case with 6 clusters. And if you want to look more in detail, you can hover over the points, and then you will see the segments that got cropped out of the source image. Left-clicking on a point shows you the segment within the source image. Right-clicking on a point performs a nearest neighbor search. In this case, for example, we have a lot of highway fences. If you perform a middle mouse click on an image or a point, you get a more detailed view of the source image with the entropy heat map on the top left, the predicted intersection over union on the top right, the predicted segmentation on the bottom right, and the source image on the bottom left. Down here, for example, we have a cluster of trucks. we could perform a nearest neighbor search on these ones. And down here, for example, we have an instance of tractor. We could continue our nearest neighbor search with this segment, which gives us a lot more tractor instances. This one, for example, is a new one. And we have another new one down here. And we could also just show the detailed view of that segment, which looks like that. That's everything to the demo. The tool can be found on our GitHub page and can be used for data exploration under domain shift. Try it out by yourself and have fun with it. After showing you qualitative results, we will now get to the quantitative retrieval results. Our results are measured using the mean average precision, short MAP, which measures how well retrieval lists are sorted in terms of relevant objects. We evaluated many combinations of different embedding networks, feature dimensionalities, and distance metrics used for nearest neighbor search. Dimensionalities of 2 and 3 were reached by first applying a principal component analysis down to 50 dimensions, followed by t-SNE. All other dimensionality reductions were performed only using a principal component analysis. The opaque bars correspond to the MAP averaged over all queries, regardless of their ground truth class, thus being weighted by frequency. The solid bars are MAP values when averaging for each ground truth class first and then over all classes afterwards. This increases the influence on the MAP of classes with very few instances. As there are multiple classes with less than 5 instances, for which it is very hard to get a good retrieval list, we get a gap of approximately 20%. In terms of embedding network choice, deeper networks show increased retrieval performance, which is probably due to more meaningful features. Despite the intuitive guess that feature vectors with higher dimensionality contain more information, we observe that retrieval results for low-dimensional feature vectors are significantly higher. Also, for nearest neighbor search, the Euclidean distance has a good advantage over the cosine similarity in low-dimensional spaces. Even though the MAP values increase slightly for higher dimensions using the cosine similarity, it still cannot outperform the Euclidean distance in two-dimensional spaces. Looking at class-wise retrieval results, we can see that concepts with a high occurrence frequency in the embedding space have higher MAP values than others. This benefits the data exploration as objects with a high occurrence frequency also have a high impact on the model performance. If we color the embedding space we saw previously in the demo application with the A2D2 annotation, we can see how well the separation of different object classes works. The 3 clusters that one could see when visualizing the estimated global density correspond to roadblocks, or in this case highway fences, nature objects and trucks. The 3 clusters are separated by a large cluster consisting of buildings and grid structure. Even small object classes like the tractors are close by another on the bottom right of the embedding space. For future works, we plan to utilize semi- and unsupervised incremental learning of new classes, attribute-based out-of-distribution detection, as well as attribute-based learning of new classes, and enhancing the detection of new objects by using CNNs that are trained to be uncertain on out-of-distribution objects. All the code can be found on our GitHub page. Thank you very much for your attention, and I'm very happy to answer questions during the online session.